last time we were working, well, we finished. What did we finish the last time? I don't remember, but we started working on arc length. All right. So to find the length of the arc so we did some kind of an analogy of constructing the formula for finding the area under the curve, which is ultimately the integral. So let me just go back real quick to that. So, the idea to find the area under the curve is to find areas of rectangles. But notice, depending on the number of rectangles, we may get an inaccurate result because we have some area going outside of the bounds of the function for which we want that area under, in this case. Well, so in order to clear these inaccuracies, what we did is add in the areas of infinitely many rectangles. Well, so we're going to do something similar to find the arc length. In this case, you might remember from yesterday's example, we wanted to find the arc length from this point to that point. So the more mini arc lengths that we get, the more accurate result we're going to get. And well, so we're just going to take one sample. In the same way that we got one sample of a rectangle in Calc 1 to define the area under the curve. And we already preset this up, so this gave rise to a right triangle for which the hypotenuse is the length of that arc. Right? And well, so we wrote this Pythagorean theorem in terms of our labels delta x of I and delta y of I. Now, what is it that we want to obtain? Because it seems like I uploaded the wrong handout. So we want to obtain this formula to find the arc length. Integral from a to b, the square root of 1 plus f of x prime, quantity squared, with respect x. And well, if we look at that formula to find the arc length, we sort of have this Pythagorean theorem going on because we have a quantity squared plus another quantity squared, and you know, because we're integrating it, we are adding infinitely many of those. The trick here is how are we going to go from this expression to that integral right here. Alright, so let's have a look. Let's see if there's anything interesting we can do about it. Alright, how can we, so somehow, okay, if you observe this f prime, that f prime is the infinitesimal version of a rate of change. Over here we have finite versions of delta x and delta y. So delta y over delta x was later defined as dy dx when we went back when we were in calculus 1. So somehow we have to have a quotient delta y over delta x inside of a radical, so we can then do a Riemann sum and turn that into an integral. Yes?
What does the I mean?
Oh, what does the I mean? For example, so in this case, when we partition this length, you know, so we have this length, this other length, that other length, that other length. So this is, let's call this L1, L2, L3, L4, you know. And in this case, I'm just taking the i's length, just any length. All right, and it could be like the 5th length, the 17th length, the nth length. All of them have to be the same length, and then we will be adding those, infinitely many of those. All right. Now the trick is, how are we going to get some delta y over delta x in here? So we need to do some factoring, and this factoring that I'm about to do, it's going to be a bit weird. Okay, let's go back to review some factoring. Let's factor x cubed plus 3x. How are we going to factor this x cubed plus 3x squared?
Take out an x squared.
Take out an x squared, that's the greatest common factor, and that's x plus 3. Alright, that's just the greatest common factor. However, check this one out. What's the factor here? Can we factor anything out? Huh? It's irreducible. Well, that's according with partial fraction decomposition, right? I agree. However, we can still factor this out. And I'm going to factor out an x squared, but how am I going to factor an x squared if I don't have any x's here? I could have done, factoring an x squared if I had an x, or maybe an x cubed, or an x to the fourth, or an x to the 100. I can factor out an x squared. But how am I even be able to factor an x squared from this expression? Yes. Exactly. So that's the algebraic mischief that we're going to do here. Alright? And you might have done this kind of factoring in Calculus 1 when you computed limits at infinity. Well, that's one of the approaches to factor out the highest power in both the numerator and denominator. So we're going to do the same over here. So L sub I will be, I'm going to factor delta x sub I squared times 1 plus delta x, or delta y sub I squared over delta x sub I. Now, do you see where are we going now? Do you see this delta y over delta x? That eventually is going to take us to the dy dx that we're looking for. So number one, let's clear some stuff over here. So we have the radical of a product. Let me write the product of two radicals. Delta x sub I quantity squared times the square root of 1 plus, in this case we have the quotient of two squares. Let me write this as a quotient of just a single and square it. And well, the square root of quantity squared, that's just going to give us delta x sub I root of 1 plus delta y sub I squared delta x sub I. Oh, wait a minute, it's the whole thing squared, right? Now, to see this in a lot easier way, how about we write that delta x sub I after the radical. So that's square root of 1 plus delta y sub I, delta x sub I, quantity squared, times delta x sub I. Did you notice this expression, how it looks like the integral that we want to obtain? This dx will be representing the delta x after we add infinitely many of these lengths, and the delta y over delta x, which is dy dx, later when we add infinitely many of those, that's f prime. It's just another way to say dy dx. There's many notations to say the same thing. So how do we justify this? Well, so we just found an expression for one length. We want to, in this case, add infinitely many lengths. Right? Well, number one. So we're going to add L. So L will be L1 plus L2 plus L3 plus dot dot dot. Ln, if you will, right? And all these infinitely many lengths. Well, we can write an expression for L1 to be the square root of 1 plus delta y sub 1 over delta x sub 1 times delta x sub 1. Well, I don't want to write all these many. Instead, I'm just going to represent this as well, L will be approximately, first it's approximately the addition of I equals to 1 to n, 1 plus delta y sub I, delta x sub I, delta x sub I. So we're going to add the first length, the second length, the third length, the fourth length, many of them. Well, but in this case, this sum is a finite sum, not an infinite sum. In order to get the accurate value, we get that by getting a good refinement, and the best refinement in this case is to add infinitely many of those lengths, and well, the approximately becomes equal once we find this as a once we write it as a limit n approaches infinity. Whoops. Delta y sub I, delta x sub I, quantity squared, which is in this case going to lead us to the integral from a to b of 1 plus f prime. Well, actually, let me write it as dy dx, quantity squared, with respect x. And well, isn't it the same as the formula we had above? However, well, we wrote it as an f prime. It's the same, f prime, dy dx, y prime, you know. And this is how we derive a formula to get the argument, right? So I don't always derive formulas. I just derive the ones that I think are like easy to do, you know, like the ones that we don't require like higher levels of math. In some cases that we would require some higher levels, so I will just give you those formulas in this case. This one is a good one. Yes?
These derivations of the formula, are we supposed to be able to do the math? Are we supposed to have seen that and been like, oh yeah, I can do this? Or is this like something that's...
No, that's just something we present to connect, you know, other ideas, like to connect how the area of under the curve using a Riemann sum was obtained. So in a similar way, instead of adding infinitely many rectangles, now we're adding infinitely many lengths in this case. And those lengths come, instead of length times width like the area, comes from the Pythagorean theorem. So that's why this formula for the arc length has the looks in the way of the Pythagorean theorem. But it's not something you will be asked to do on the exam or supposed to know how to do. It's just something that we do in lecture to see connections between things you've done before. So let's go ahead and do one example. So find the length of the arc of the curve f of x equals x to the 3/2 between 0 and 1. Alright, so number one, the formula to find the arc length, that's the integral from a to b times of the square root of 1 plus f prime quantity squared with respect x, right? So, well, our formula for arc length is calling for the derivative of the function. Yes? Yes, I just realized that in the morning section, so just change, for those of you who have the handout, just change it for this. Instead of going from 1 to 4, we're going from 0 to 4. Just change it. So let's find the derivative of the function. So the derivative of f of x equals x to the 3/2. That's going to be, well, f prime 3/2 x to the 3/2 minus 1. That's 1/2, which is 3/2 root of x. And I recommend you use the radical form right here, because something cool is going to happen once we write down the integral. So this will be the integral from 0 to 4 of the square root of 1 plus the quantity, the derivative, that's 3/2 root of x, quantity squared, with respect x. Okay, so careful with squaring this term right here, because the square is going to affect both the coefficient 3/2 and also the variable factor. So on the one hand, well, this remains 1 plus, okay, 3/2 quantity squared, that's going to give us 9/4. And what happens when we square a radical? Don't they cancel each other, leaving us with simply x, and then with respect x. And well, this integral should be good to be integrated using a simple g substitution. So, and that's because we have a degree inside of the radical. If we do du, that will take that polynomial to a degree 0, which is basically what we have multiplying with the dx. So it should work. All right. So let's set u equals to 1 plus 9/4 x, and then du equals 9/4 dx. This means the x will be 4/9 du. All right, so again, okay, what are we doing in this case? So I don't think I did this before, or maybe I did, I can't remember. So technically the correct way to evaluate a definite integral that goes through the process of a u substitution, we wouldn't just be changing the function and the differential to the world of u. That is, that would be the square root of u and then du times 4 over 9. Technically, we have to also find the equivalency of the limits of integration in the world of u as well. So we need to change the corresponding, the 0 and 4, their equivalents in the world of u. How do we do that? Well, we're going to use this u expression and evaluate u at 0 and evaluate u at 4. And in fact, that my advice is that you change the limit to the world of u in this case, because with doing this, it's going to save you a lot of work. Instead of it's going to save you the back substitution and the fundamental theorem of calculus to plug it into many expressions. You'll see how this is going to work. So u at 0, so that's 1 plus 9 over 4 times 0, and 1 plus 9 over 4 times 4. So this will be, well, 0 plus 1, that's 1. And here we can cancel the 4s. That's going to leave us with a 9. But 9 plus 1, that's a 10. So we're integrating from 1 to 10 in the world of u. Alright? So let's do the whole problem in the world of u. So let me take the 4 9s outside of the integral and change this radical into rational exponent so we can integrate it. So that's going to be 4 over 9 u to the 3 halves over 3 halves, and that goes from 1 to 10. So having the limit from 1 to 10 will avoid the back substitution and having to write too many terms when we evaluate upper limit minus lower limit. So 2 good reasons to change this limit. Number 1, well, because technically that's the correct way to do it. You change the function to the world of u, so we have to carry the limits to the world of u as well. Also help us skip a lot of the work. Well, a few things at a time. So dividing by 3 halves is the same as multiplying by 2/3. And let me leave this u to the 3 halves for a second. So 2 times 4, well, nothing is going to reduce, unfortunately, here. So this will be 8 over 27. That's going to be 10 to the 3 halves minus 1 to the 3 halves. Okay, so we need, when we have numbers like this, we need to simplify them to lowest terms. In particular, these rational exponents are going to give rise to weird radicals that we need to simplify one way or another way. So, well, how are we going to do this? Well, let's recall the properties of radicals. Number 1, whenever we have a to the m over n, this means a couple of things. Number 1, again, the denominator of the rational exponent tells us the index of the radical, so that's the end root of a to the m, or this is n times, the end root of a to the m power. Well, which one are we going to use? Well, depending on what we have. So the question is, well, number 1, the denominator, which is 2, it's telling us that we will have to compute square roots. So the question is 10 to the 3rd power going to be a perfect square? Not, right? That's not going to be the case. So if that were the case, we would have used the latter version, take the square root of the perfect square and then raise it to whatever power, so when we have like 5 to the, 2 to the, well, never mind. Yeah. So what are we going to do here? So we're going to write 8 over 27. I'm going to do this first version. That's the square root of 10 to the 3rd power minus, well, 1 to any power is simply going to be 1. Alright, so no worry about it. Now again, 10 to the third power, it's not a perfect square. However, how about we write square root of 10 squared times 10? And in this case, there will be a factor of a perfect square that we can simplify. So this will be 8 over 27, 10 root of 10 minus 1. And that's final answer. Right? The reason I go through all these details here is because I don't think WebAssign is going to like these answers right here. Most likely it's going to be looking for simplified radicals, all right? We're going to do a lot more of this when we get to the next section in calculating surface areas. In the meantime, let's have a look at the next example. And the next example, it's going to be a bit heavy on the algebra. Nothing you haven't seen before anyway, but at first glance, when we look at the setup, first it will freak us out. Question? Yes. Y equals, okay, let me go to function mode, and so this will be x to the 3/2. So, graph. So we're finding the length, how far along the curve we go from 0 to 1, 2, 3, 4. That's the distance, which is 8 over 27 times 10 root of 10 minus 1. Alright? Let's look at the next exercise. So find the length of the arc of the curve y equals x cubed over 6 plus 1 over 2x. So number one, let's write this function in a nicer way so we can differentiate it. Okay, so that's y equals 1 over 6 x cubed plus 1 over 2 x to the negative 1. Only then we would be able to differentiate this function. So let's go ahead and do that. Y prime, that's 3 over 6 x squared plus, well, actually minus because the next exponent is negative, 1/2 x to the negative 2. 3 over 6 reduces to 1/2, and that's 1 over 2x squared. Actually, I'm going to write this x squared over 2 instead of a half for a big reason. Alright, let's find the arc length. From integral from a to b, square root of 1 plus f prime quantity squared with respect to x. So that's the integral from 1 to 2 this time. That's 1 plus x squared over 2 minus 1. Actually, I'm going to leave some space here. You'll see why. Minus 1 over 2x squared also. Quantity squared. Alright, how are we going to go about this madness? Don't even try use substitution because good luck finding the derivative of that using, I mean, it's not going to be that crazy anyway, but it's going to be useless because we don't have anything multiplying with the dx that could potentially stand the u du part. So in this case, we're going to use algebra to simplify this expression. Well, notice we have like a multi-layer function. So we have a radical, then inside we have a polynomial, and one of those terms in the polynomial contain parentheses with another, well, it's not quite a polynomial but has more terms. So let's simplify this and make it look like a single fraction. So we have the 2's. How about we multiply numerator and denominator by x squared? That way we can combine these fractions together. So L equals to the integral from 1 to 2 of the square root of 1 plus x squared times itself, that's x to the 4th minus 1 divided by 2x squared quantity squared dx. So what do we have? We have a quotient. For that quotient, I'm going to distribute the power 2 right here so we can further simplify the whole radicand into a single rational expression? Well, so this will be the integral from 1 to 2. That's the square root of 1 plus, okay, x to the fourth minus 1, quantity squared, divided by 2x squared. Quantity squared, isn't that going to be 4x to the fourth? However, again, I need some space because I'm going to do a combination of fractions, all right, with respect to x. So you can think of this 1 right here as 1 over 1. In order for this to combine and to do another combination of fractions together. So, well, it looks like we need to make sure that both terms have a denominator of 4x to the 4. So multiply 4x to the 4th in the numerator and divide by 4x to the 4th. So now that we have both denominators the same, we can put this into a single fraction. So 4x to the 4th plus x to the 4th minus 1 squared over 4x to the 4th. Okay, let's work on the numerator of this radicand first. So number 1, we have a binomial quantity squared. There's a couple of ways to go about a binomial squared. Of course, you can write it as the product of the quantity and itself and do the foiling. However, that's going to take some time, and I discussed that before. Instead, I will use the binomial square formula, a plus or minus b quantity squared. So that's always a squared plus or minus, depending on the case, 2 times a and b plus b squared. So let's apply this to this binomial here. So this will be the integral from 1 to 2 of the square root, okay, that's 4x to the 4th plus x to the 8th, x to the 4th times 1, then times 2, that's 2x to the 4th, and then 1 squared, which is 1. Whole thing divided by 4x to the 4th. That with respect to x. Let's combine like terms in the numerator of the radical. So we have this 4x to the 4th and minus 2x to the 4th, and that's going to give us 2x to the 4th. Square root of, well, let me write this in descending order of powers, and plus 2x to the 4th plus 1 divided by 4x to the 4th with respect to x. All right. Okay. We still have to simplify that numerator. And well, if you observe the numerator, we have something squared plus 2 times something times 1 and then the b squared. But if it's not too clear, well, let me go back to perfect square binomials. For example, when we have x plus 3 squared, x minus 7 squared, that's an x squared plus 6x plus 9 equal, and over here we have, let me add a 2. That's 4x squared plus 2 times 2, which is 4 times 7. Is that 28? Actually, minus 28x plus 49. Now, so that's the expansion of a binomial squared. Now, what if we have in this case the reverse? For example, x squared plus 14x plus 49. How can we write this as a binomial squared? X plus 7 squared. This is a perfect square trinomial that can be rewritten like this. What about x squared plus 2x plus 1? X plus 1, quantity squared. What about x to the 8th plus 2x to the 4th plus 1? So that's the integral from 1 to 2 of the square root of to the fourth plus 1 quantity squared over 4x squared with respect x. Alright? Well, what do we have now? So inside of the radical we have the quotient of two perfect squares. So at this point we can use the radical, the quotient rule for radicals, which is in this case the integral from 1 to 2, the square root of x to the fourth plus 1 quantity squared divided by the square root of 4x to the, actually this is supposed to be 4, right? Good news, these are perfect squares. Well, what's going to happen then? Well, so radical cancels the square, and that's going to give us the integral from 1 to 2, x squared plus 1 over the square root of 4, which is 2, and the square root of x to the fourth, which is x squared. And what's this? We can split the integral into two integrals here. That is, x, let's do one thing at a time. X squared over 2x squared from 1 to 2 plus 1 over 2x squared dx. That's what which one? Oh yeah, this is x to the fourth. Yes, thank you. So what's next? Well, so x to the 4 over x squared, isn't that how about 1/2 x squared? This time I'm going to need the 1/2 notation at the x over 2 so we can easily integrate the x's. And I'm going to write this plus 1/2 x to the negative 2. Well, the integral of these two terms, that's going to be 1/2 x cubed over 3 plus 1/2 x, add 1 to negative 2, what do we get? Negative 1, and divide by that same negative 1 in the denominator and evaluate this from 1 to 2. Well, first things first, let's clear the mess with the signs and negative signs and the negative powers and the coefficients. So this is 1 over 6 x cubed, and then plus a negative quantity that should be minus, and that's 1 over 2x evaluated from 1 to 2. Well, the rest of the problem is fundamental theorem of calculus, f of b minus f of a. So this will be 1 over 6, and that's 2 cubed minus 1 over 2 times 2, that's f of b, minus the f of a, which is 1/6, 1 cubed, minus 1 over 2 times 1. And let's simplify this. So that's 2 cubed, which is 8, that's 8 over 6. And I know this reduces to, what's that, 4 over 3? Let's keep it like this, minus 1/4. And then careful with the last two terms, because when we distribute this negative sign, the first term will become negative. That's 1 cubed, which is 1. But 1 times 1/6, that's just going to be 1/6. And then minus, that's going to become positive 1 over 2, that's 1/2. Alright, so how about 6th with 6th and 4th with basically 4ths, right? So 8 minus 1, 7 over 6, and have a half, take away a quarter, 1/4. Alright? And well, to combine these fractions together, I'm going to multiply by 4, divide by 4. I'm going to multiply by 6, divide by 6. And that's 28 plus 6 divided by 24. And 28 plus 6, isn't that 32? No, 34. 34 over 24. And both numbers here are even. That means they can be divided by 2. That's 17 over 12. And that's final answer. Let me zoom it out so you can see the whole thing in case you missed anything. And guys, this is all I have for today. Next time we're gonna cover, or we're gonna start working with surface area. We're gonna do algebra like this. So bring coffee, Rockstar, whatever, Red Bull, whatever keeps you awake, because we're gonna get busy next time. All right? Have a great weekend. See you on Monday. Yes.
We have an extension of our homework.
Send me an email so I can have it on record. Right?
Oh, okay. And what would like you'll give me a day or what?
Maybe a day or two. Well, how long do you need?
Yeah, like another.
How about
another
Sunday
day.
midnight?
Huh?
Sunday midnight? How about that?
Yeah, that'd be great.
Okay. Just send me an email through Canvas.
Okay. Thanks, Professor.
You're welcome. Yes.
Are we gonna need to remember the equation?
Which one? Oh, for the arc length, yes.
Okay.
Most likely. Yeah, the easy ones, just remember them. The harder ones, those might be provided on the test.